and start with this. So, okay. So I get that a lot of people are tired, but, you know, please try to follow along with this, lecture as best as you can. So, yeah. Sorry. Let me go ahead and put this onto there. So it's also important to note that basically these next 2 weeks might be very tough for you. Okay? So the first thing is because your first exam is coming up. Yeah. So I like to do my exams every 5 weeks for this class, and if you've been counting, this is week 4. Now we'll see. It might get pushed back to week 6, but week 5 is probably when. So next, I'll let you know basically by Wednesday whether you're going to have it next week or the week after, and it should cover basically basically it will cover array list and linked list and coding with that. Now, for those of you who have not been in one of my classes before, what that means is that you will be getting a practice exam before the actual exam. Now, the practice exam, the way it works is that the way I originally designed my practice exams is I made twice as many questions as I need for my first exam, and then slapped half of them in the first exam and slapped the other half in the practice exam. So, the practice exam is a very good facsimile of your actual exam. So if you can do well on your practice exam, you'll be able to do well on the actual exam itself. And so the first thing is that you've got this exam. I'm probably going to change up problems because I'm sure some of you know what the exam looks like at this point by virtue of having had friends go through this class. And that's just what happens with exams and why we don't make practice of handing our finals back, because then we don't have to create a completely new final each semester. Now, so I'll probably be working very hard to do this. Again, I'll see where the time labs go, and we'll probably do our second time lab a couple weeks after our first exam. This will give you a pretty good idea of how you're doing in the class in the beginning. Now, it's around this time where basically this class, I think, should feel the hardest. It's not the hardest it's going to get, but it's going to feel like it's the hardest. Like some of the material later on is a bit more complicated, but just simply because we're still working with linked lists right now and making sure we understand the way linked lists work, it's going to be the hardest right now. Also, this week is when you get your that homework where it makes it feel like the hardest, even though this is not the hardest assignment. It's just simply new, and that's just the Josephus problem. So you're going to get basically the homework and the exam. The homework will be due before the exam because it's really good practice for you to understand how it works. So I'll give it on Friday, and basically you'd be due. Well, actually, technically, it would be due that Saturday right after the exam. So, and if people need more time, then might extend it. But just let me know how you're doing on that. So your first exam is coming up as the end result, and you've got your first actual assignment that's something other than complete these problems, kind of assignment. So let's go ahead and get started with our lecture. So we were dealing with linked lists last lecture, and our linked list, as you remember, is essentially the special kind of list. This weird kind of list too. And that's because it basically grows and shrinks as we need it, right? It doesn't work like the array list where basically we have an underlying array. Here, the way it works is that we use nodes, and the nodes, the way I originally put it is that nodes are essentially they aren't nested Russian dolls, right? Even though it seems like there's a node object and each node object has another node inside of it. That's not the way it works, right? This is a memory location over here, and it stores the memory location of the next node object. So this is a scavenger hunt, right? This is the item, right, that's being stored, and this is the location of the next node where we can find the next item being stored. So we just simply follow the nodes through memory to find the proper to find out where everything is. Okay. Once we're done following everything through memory, the final node, it has a pointer of its next pointer goes to null, and then we're done. Okay. So that's the way that these note that these guys work. Okay, so where were we last time? I think we were just creating, we showed that basically we could do an add method, and we created an add method, and we showed that basically we can add to the head of a linked list very easily. And I took a different paradigm this time. I created a new node called, so how did the add method work? We said, we want to add a node to this index. Even though we've got this chain of stuff, we still refer to like where everything is in the index. So the head is index 0. So we wanted to add this item into this list. If the index was less than 0, we threw an exception. If it's greater than 0, if it was greater than the size of the list, we threw an exception, right? Because we could add to the last possible, we could add to index size if we wanted to add something to the end. Okay. The first thing we had to do to make sure that, and this is a common mistake I've seen in previous exams, is, and the common mistake is leaving this out, we have to store the item in the node, right? We can't just, the item doesn't have next pointers, right? It doesn't have next pointers. It has a, you need to store it in a node so it can be attached to the list. And so I call this one adding, right? Because we're adding this one to the list. So if this was index 0, then what we were doing is that we'd say we're going to take the memory location of head and store it in adding.next, right? So if we're adding to index 0, that means that adding needs to become the new head. So the first thing we do is we attach it to the current head, and then we make adding the new head. So let me just go ahead and draw that out on the board in beautiful orange, apparently. Okay, so we've got a node here, and we've got a node here, right? And this, right, it's got some data, and this one's got some data. We've got, now this node is head, and when I put a label head down here, what it really translates to is I've got some variable up here, right, called head, and it's storing the memory location of this node, right? That makes sense? It's storing the memory location of this node. So when I put the label head down here, that's what I'm doing. I'm saying that this is the node that head is being stored in. Let me just make sure I don't have something slightly different. So I could have sworn we really went to work and got all the markers I put in here. Oh, haha. There we go. You came prepared. Okay, so now we want to add this new node called adding into there. Okay? And the first thing we need to do is that we attach it, right? So we do the adding.next is equal to head. We say we're storing the memory location of head in adding.next. And then we're going to make, then we say head is equal to adding. And what that does is that takes this variable I said over here, which was head, and points it towards adding. Make sense to everybody? Okay. The next thing, okay. So what if we don't want to add into the middle? What if we want to add, say, anywhere else? So, let's see. Normally I do squares, but I'm trying to do rectangles because those seem to be more canonical. Let's go ahead and say that. Right? So this is at index I. This is I plus 1, right? These are the indices. I plus 2. That makes sense to everybody? I'm not using... So say we want to add it to... We want to add our node to... Actually, let's go ahead and adjust this so that is not often. Let's say we want to add our node to index I. So we've got I minus 1 and I plus 1 over here. Okay? So say we've got a new node over here, and we want to, and this is our adding node, right? Okay. We created our nodes over here, and what we want to do is now we want to add to this location. Well, so what we do is that we grab the node before the index we want to add it to. Okay, so we say that adding, so we want to add adding to I, so we don't grab I. We use getNode to grab I minus 1. So we call this guy before now. So we've got a memory location that stores his location called before. Okay, we move, and then we say, we don't move him yet, because if we move this first, we'd lose the rest of the chain, right? Instead, what we always do is that we connect adding first. So we connect adding, since the node currently at I, if we're adding the node adding to I, then I will be his next node, right? So we say that his next node is before's next node, right? So his next node is before next node. So that's the line right over here. Adding.next is equal to before.next. And then we update before.next to have it point to adding. So we store adding in before.next's variable. So now we go from them both pointing to the same node, and now the indices update like this. Now this one's I, this one's going to be I plus 1, this is going to be I plus 2. Right? They just kind of automatically update. Okay, and then we also always want to increment the size. Now notice that this, if we're adding to the head, that took constant time. It was an O of 1 operation. Didn't matter how big the node was. Here, though, this is going to take O of n time because the getNode function uses a for loop that, worst case scenario, has to travel through the entire list. And then moving around, manipulating the pointers, that takes a constant time operation. Now, if we create a custom thing where basically we want to add 1,000,000 things to the to the middle of the loop, to the middle of the array, we could iterate to the node in the middle and then add those 1,000,000 things there, and all those 1,000,000 things would be added. We'd only have to loop in once, and then we could add the 1,000,000 things in, right? And so all those additional operations would take a constant amount of time. Basically, as soon as we grab the node and if we save its location, like we save head, then every addition operation would be free after that. But most of the time, we don't save anything like that. Now, what we'll do when I get to after I go over remove is that I'll update these all so that they work with a tail, so we can also add to the end in constant time. But for right now, I want to keep this fairly straightforward, just dealing with a head, no tail right now, because I like keeping the method pretty simple. Okay, so this was add. What about remove? Okay, go ahead and draw this something similar. We're going to deal with removing the node, the head from the list. Okay, so we want to remove the head from the list now. Okay, so we've got a couple of nodes here. We've got your first node over here. That's our head, right? You've got heads next, and then you've got whatever comes after that, which really doesn't matter too much, because really what we concern ourselves with is just head, right? So this is head, right? And if we want to, let's say we want to remove this item, right? Well, what needs to happen for the list to adjust? Okay, first things that needs to happen at the end when we write add, we got to remember if we're moving a node, we got to just decrement the size. So let's not forget to do that, because I was going to totally forget to do that. But otherwise, for removing the head, what has to happen? This needs to become head, right? If we're removing this guy, then all that really needs to happen is that this needs to become head. So we'll update this second node to be head, right? And then what will happen? Do we really need to take care of this guy? Well, once this node is head, garbage collection will take care of this for us. This guy will be alone. It's not going to have anybody storing his memory location for him, so he'll be inaccessible. And now in C, this would be a problem because we'd have a memory leak, right? But in Java, with and other programming languages that have automatic garbage collection, it's automatically going to free up this space for us and take care of deleting it for us. And so now this is the head of the list, right? The head is dead. Long live the new head. Okay. So that's really, so removing is actually fairly straightforward if we understand what's going on there. So let me just redraw this back on because I'm going to refer to it again in a second when I do this. Okay. And before I forget, let's just finish up the last add method, right? We've got to add this item, and this one should always return true. And what we wanted to do is that we'll just simply overload, we'll call our overload method and simply add if we want to add it to the end, that's adding it to index size, right? So we don't really need to do anything over here. Add, do this dot add to index size the item we want to add. Okay, so now we just need to do the remove method. Okay, public E, because it's always polite to give the thing that we're grabbing back. Remove, and we want to remove some particular index. If we need to remove some particular item, we can find the item in the list. Then we can remove and find out what index it's at. Then we can remove it. So we'll go ahead and remove index from the list. Let's go ahead and make a E2 return. Right, that's the value we're going to return, and we're just going to set that to null to begin with because I don't like having errors in my code. So I like to quash these errors as soon as possible. So I'm going to say we're going to save to return, and then we'll return it. There we go. We're error free now. Okay, and since I have it kind of bookended like that, meaning I have the beginning and end, I can remember that after a successful remove operation, I need to remove the size. Got to reduce the size, right? And let's just add one more thing, right? Let's go ahead, and I'm just going to go down here and copy this, right? This bit over here to make sure that basically, I always like doing this just to make sure that it's a valid index, so we don't have to worry about if somebody's trying to grab the wrong index from us. Okay, that makes sense? So first things first, just like the add method, my first condition is I check to make sure that I can actually remove the thing I'm trying to remove. That's my first condition. If index is less than 0, I can't remove it. If it's greater than or equal to size, well, that isn't the index that currently exists, so I can't remove it. Greater than or equal to size. Okay, so we set E to return equal to null because once we get the node, what that will be depends on the condition. So again, we're going to set it up. It's just completely symmetrical in terms of format to our remove method. If the index we're removing is equal to 0, do one thing. Otherwise, it's every other condition, right? That's all we really need to do. So again, we're focusing on head. So first thing let's focus on the value we want to return. Well, if we're removing index 0, right, we need to remove the head, right? So we want to store what's currently inside the head. So let's say to return is equal to this dot head dot item, right? This head item is what I want to return. Make sense? Okay. Now, what I now actually have to do is remove the head of this list. So head is equal to what? That's the question. What should I set head equal to? Well, I could do something like this and go next. So I want it to be the next node in the list. So I can break it up like this. I'm going to remove this line in a second. Next node is equal to head.next, right? The next node in the list is equal to head.next. And I could say the head is now equal to next node. But why not just cut out the middleman, right? Instead of saying next node is equal to head.next, we can say that, and then head is equal to next node, we can cut out the middleman and say head is equal to head.next, right? And all that's saying is that, let's go back, let me just go ahead and restore this over here. right? The next node is head.next. So we would take the memory the memory location of the next node, of the node after head, the memory location of the node after head is stored in head.next, right? So we store it in next node, and then we say head is equal to next node, or we could simply say, as I did over here, head is equal to the memory location of what comes after it. So we take the memory location of what comes after head and store it in head. So this this is just like I is equal to I plus 1, right? We're taking the value on the right and storing it on the left. And this is basically the remove method is where if you don't understand how these update operations work and how variables can modify themselves is where it starts getting a bit dicey, which is why I put this over here. Okay? So now another question that someone might be asking is, well, wait a sec, what if there's only one thing in the list, right? It doesn't matter if there's no things in the list because that would be caught over here, right? We can't remove something if there's no things in the list. But what if there's only one thing in the list? What's the only thing here? For a singly linked list, the way we've written it, it doesn't matter. If there's only one thing in the list, then this is head, right? So we store what's inside head, and then head is equal to heads.next, and heads.next is null. So head is equal to null, which is what we'd want with a empty list. Okay? Okay, so, all right. Now for this one is where it gets fun. From my perspective, this is where it gets fun, this next one. And so if you are dealing with a hangover from last night, I'm sorry that your head is especially going to hurt now. But then again, you can always come back to it when you're more sober. Let's go ahead and so here again, what we're going to need to do is that if we want to remove, let me just draw this on the board. Okay, again, so here we've got our 3 items. Let's say we want to remove index I again. Okay, so we've got I minus 1, ... over here, and then we've got I plus 1. So I want to remove this victim, I guess, okay? Okay, so now, again, what I need to do is I have to actually iterate to him. I have to actually find him, right? And I don't necessarily want to find him because I can't just, if I let him be the node, right over here to remove, if I get his memory location, I can't really do much with him, right? I can't, because what I need to do to remove him is to get this node to stop pointing at him, right? To remove him, I have to get this node to stop pointing at him. So again, what I have to do is get the node before, okay? Now, what I have to do to remove him now is I need to take this, this points to I right now, right? If I want to remove I need to point to the node at I plus 1. So that's literally what I'm going to do. I'm going to skip over him and have this point here. Then garbage collection is going to take care of him. Does that make sense to everybody? Okay. So I'm going to let garbage collect. So I'm going to get the node before, just like I did with add. Okay. But instead, what I'm going to do is take this guy and remove him. So I'm going to break it up into multiple steps, and then I'm going to make it more efficient by just doing it by doing it with one get node call. So I'm going to do it with 2 get node calls. So the code I'm going to write is always going to do the same thing. I'm just going to simply update it as we're working here. So let's go with node E before and node E to remove. So the node E to remove, this one is going to go away eventually. Okay, I'm just leaving this one here for context. So the node before the one I want to remove, well, I can use that get node index minus 1. And remember, that's not going to fail for the same reason it won't fail in add, because it would only index minus 1 would only fail if the index was 0, which it's not going to be because of the conditions. Okay? This node is guaranteed to exist because index has to be in range. So that isn't going to fail either. Right? So this is the node I'd like to remove. Of course, I don't have to do 2 get node calls because get node calls take O of n time to do. So rather than doing 2 O of n calls, I could just simply say the node to remove is before.next. right? Before's next node is the node to remove, right? Okay. Then to return is equal to remove.item, right? Right? It's the item that we're it's the node that we're removing gets its item. That's an item I'd like to return. Okay, so that's just all the stuff getting set up to make sure that we saved everything. Okay, and eventually I'll condense this to just 3 lines as opposed to the 4 that we have. So now to actually remove the item, to do that we have to modify before's next pointer. Right? Before's next currently points to remove. It's a node that we'd like to remove. It currently points to the ith node there. We'd like it to point to the ith plus 1 node. So we can say before.next is equal to remove.next. Right? Does that make sense? And that's what's going on over here. We have this point. We have this node. We have this .next, and rather than storing the memory location of I, it stores the memory location of this node's next node. Right? That makes sense to everybody? Okay, so let's go ahead and see if we can't do this now without using the toRemove at all. Okay, so let's get rid of the toRemove variable. Okay, remember toRemove is before.next, right? So the item I'd like to return is what? It's before, right? It's before's, so it's .next.item, right? It's before the node after before, right? It's the item in the node after before, okay? Now before.next needs to point to what node? Well, before.next is the node after before, and we want to go 2 steps. So what can we put? Right? What is toRemove? toRemove is what? What do we set it to? But we set it to before.next, right? So before.next.next, right? Before, let's go ahead over here. Before.next.next. Right? Yeah, it just simply goes, it's the memory location stored in the node before.next. What is before.next? It's the memory location stored in before.next. It's a node. So there's a reason I use .next as opposed to just other node, because it allows you to advance. Now, how do doubly linked lists nodes? Sorry, so these are singly linked lists. How do doubly linked lists work? They have an additional pointer called previous. So you have next and previous as well for those. And one of my favorite test questions that I have, which is like on the first page, is here's a linked list. Start at node A, which node. So now we start with a.next.next, previous.next.next.next, previous. Which one am I pointing at, right? So those are some questions I really like. Yeah, so it's just, and it's fairly easy if you understand that this is just a line, this is just a chain. You're starting at before, .next advances you 1 up the chain, and previous advances you previous up the chain, and this adjusts what the arrow is pointing to, right? This is changing what the arrow is pointing to. Okay, so that's how we figure these things out. All right, so that's add and remove. So let's go ahead and test these things out. So first off, we had this one. So let's go ahead and see what we've got here. So we've got add 5, 4, then 3, then 2, then 1, then 0. So we've added everything in reverse on here. Now I can do L.remove, and I want to remove the 0th thing at index. Let's go with the thing at index 2, and then we'll print out the list. Okay. So So here's the list. Let's remove the thing at index 2. We still got, and we know this, we still had the rest of the list, and we didn't, that it still works because of the way the print line method works, right? The toString method, it goes through everything still in there, right? So we didn't lose anything additionally because if we did, current.next wouldn't be able to find it. Okay, let's go ahead and remove index 5 from the list. So that just removes the last thing from the list. And now let's go ahead and remove index 0, and then we'll remove index 2 from the list. So just to make sure that basically it still is doing fine. So index 0, and then basically remove. You always want to be able to make sure you test multiple removes because to make sure that you didn't somehow mess stuff up in between removes. So we removed the 0th item, and that made it 4, 3, 2, 1, and then we removed this 0. Then we removed the second item, which was 4, 3, 2. So we removed the 2. All right. So now on the exam, assuming I changed the exam, so let's assume for the sake of argument that I haven't changed my exam, and I get too lazy and I don't actually change my exam. The way the exam worked is that I told everybody in advance that expect that 15 points on the exam would be writing this exact method right over here, the add method, right? Just pretty much this verbatim, right? But it is easy enough to memorize, and a lot of people have. So I'm probably going to change it up this semester a bit. But this is what one of my questions were on previous exams, and same with the remove. All right. The only issue here is that we can only add to the head in constant time, and I would really like to be able to add to the tail in constant time as well. Okay, so let's go ahead and modify this. So we need to make a private node e tail as well. Okay, and this will require adding a 4th condition if we count the if statements as a first condition. So in the constructor now we do something similar. And what's nice is that so many of these variables are 4 letters, but without being 4-letter words. Size, tail, head, indexed. So let's go ahead and modify add. All right. So now we have to add a couple of we have to add one really weird condition. Okay. Okay. The weird condition we would have to add is we have to add a condition here. What if the thing we're adding is the very first thing in the list? Okay? What if size is currently equal to 0? Okay? What happens if the size is equal to 0? Because if we don't have this, okay, what's going to happen if we want to keep track of the tail? We don't set up the tail anywhere. The tail needs to be set up pretty much at the beginning, because at the very beginning of the list, the head and the tail are going to be the same node, right? And then as we add stuff to the head, we adjust the head. And as we add stuff to the tail, we adjust the tail. Does that make sense to everybody? Yes? So I'll come back to that. And then I'm going to add in a second else if condition over here. So I lied. We need 5 conditions now. Okay? Else if index is equal to size. Right? So now what are our 5 conditions? Now these are the 5 conditions you'll need to do for your homework. Your 5 conditions are, what if we are adding, to the first node in the list, to the first location. What if we're out of bounds? What if we're adding the very first item to the list for the first time, right? Okay? And notice how these these conditions are mutually exclusive, because you can be adding, because the item you're adding to size, when you're adding something to size 0, you're adding it to index 0, which also happens to be the size. So it's very important that these things are else if conditions, right? Okay, so this one is adding the very first node, adding a new head, adding a new tail, adding anywhere else. Okay, this one's not too bad. Here we would say head is equal to adding, and tail is equal to adding. Nothing too nefarious over here, right? Does that make sense? It's, if it's the first node in the list, right? I'll just draw it because even though it's really easy to draw, if I'm adding a new node to the list, it makes sense that this item is both the head and the tail for the list, right? Everybody following so far? Cool. Okay. Then, what are we going to do? We need to, what if we're adding to the end of the list? Well, if we're adding to the end of the list, let's go ahead and draw that out. And I'll just reuse this one over here. This drawing over here. This node is the tail, right? If I'm adding a new node and I want it to be the new tail of the list, right? What do I need to do? Actually, on this one, this is pretty easy. All I have to do is just connect this guy to the end of the list. I don't need to try to connect him to anything else because this next node is already null, and it's going to remain null. So I just simply say tail.next is equal to adding. Now, even though none of these conditions were hard, you can see why when I had it on the exam and told people to do this on the exam, that I didn't have a tail node in there because the 5 conditions does make it a bit tricky, right? Even though this condition really isn't that hard. Tail.next is equal to adding. Oh, and then I have to make this node the new tail, right? The adding node the new tail. So tail is equal to adding. And notice how symmetrical that is to the first one, right? To this condition. And that's it. That's all we need to do to be able to add to the tail in constant time. So let's just make sure it still works. It still works. Okay? Yes? What is tail.next? This one over here? Yeah. Yeah, we're simply saying tail.next. Take this memory location. Take the memory location on the right, which is adding, and store it in tail.next, which makes this draw. Does that make sense? Tail.next is initially null, right?
So when you're getting tail, you're getting the current tail.
Yeah, the current tail of the list. The current last node in the list. And we're always making sure that's the last node in the list because we initialize it over here, right? Let's go ahead and just draw what happens just to make sure this happens. Now, because this is part of the homework, I'm going to leave this as as professors are so loath to say, or you loathe them for saying it, I should say. I'm going to leave remove as an exercise to the reader. Specifically, it's going to come up on these 5 conditions come up in the homework, but I have them like clearly listed for you and marked out for you. But let's see what happens if we want. So let's see what happens. First node I want to add. Right, I'm adding the first node. It's got to get added to index 0, which happens to be the size of the list. So that's going to mean. So that says that we do head dot adding, and head is adding and tail is adding. So this is both adding, and then we make it the head, and then we make it tail. Okay. Now suppose we want to add a new head to the list, okay? New head to the list. We say that this node is adding. We say store head in adding.next, so we attach it, and then we make this node the new head. Okay, and now this guy remains the tail, right? That doesn't change. What about adding a new tail? Make this node, we call this one adding. We say tail.next is equal to adding, and make tail equal to adding. Right? And that confuses people sometimes, right? Tail.next is equal to adding, and tail is equal to adding. Well, what we're saying is that we're saying the current node that is tail, its .next pointer, I'd like to store the memory location of adding in it. Okay? And now I'd like to store the memory location of adding in tail, so that adding is so that now when we call tail, it is adding. Okay. And then if we want to remove it, if say we want to add the index 2 over here, so we would get the node at index 1, first thing we do is attach this to the node currently at index 2, then take the node at index 1 and point it to the new node that we've just added. So that's how linked lists work, basically that's how linked lists work, essentially. You should definitely expect some kind of basic quiz on this in the beginning of the next lecture on Wednesday. But that's all there really is to linked lists. I'm not going to really go over the contains method. All you have to do is just scan, is that you iterate through each item, right? And go through each item and check to see if it has the node in it. But otherwise, it works out pretty well. All right, but this is not typically how nodes are. These are typically not how linked lists are implemented, singly linked. They're nice and memory efficient as a result, though. But sometimes it's more. But a lot of times it's convenient not only to go iterate through forwards, right, in one direction. We also want to be able to go in another direction. We want to be able to go backwards through a linked list, right? That makes sense to everybody? So as a result, we're going to do doubly linked lists as well. So let's go ahead and let's go ahead and make sure we understand these through a doubly linked list. So let's go ahead and create a new class called, it's going to be called double linked list. Okay, so let's see where this, now a lot of the stuff I'm going to be able to just steal. Like one of the things I'm going to be able to steal, because the print line always works in the same direction, and the get node also always works in the same direction, is I'm just totally going to steal the get node and the toString method. Those are not going to change. Okay? These things are not changing over here. Okay? So I'm just going to copy them in. But we need to make our own new node class. So let's go ahead and make a private static node class node E, because the node in here is going to be different than the node that we used in the previous example, right? It's going to start out similar, where we have an item, right? We have a private item that we store inside of the node. But doubly linked lists, they use their nodes are doubly linked. So we have a next, but we also have a previous, which is just going to be, which I'm just going to use the 4 letters for, just so that it lines up nicely with everything else. And we're going to call it prev. Okay? So we not only have a next, we have a previous. So as a result, when we draw our doubly linked lists on the board or on paper, which you should totally be doing, because that actually sounds like a fantastic question, making you draw linked lists or draw the steps for what happens in linked lists. A linked list will look something like this. And I think I'm going to forego with that arrow. I'm just going to use boxes right now for this one. So they have their next pointers, which I'll always put on the bottom, and then they also have previouses, which I put on the top. Okay? And now this node, his next, points to null. The last node, the tail of the list, his node will point to, his end will point to null. Or his next will point to null. And the head, as you might gather, it points to previous. Right? Sorry, its previous is null. So the head, its previous is null, but its next is good, and the tail's next is null. Otherwise, it's fairly the same. And here we're going to have to use our 5 conditions. Okay? And let's go ahead. Otherwise, we're going to take in the exact same constructor as we did otherwise. So the public node E item, assuming it can spell item, which I didn't think item would be hard to spell this morning, but I was wrong. Okay, so this dot item is equal to item. Okay, so now let's see what else we need to make this work. Well, we also need, so otherwise we're keeping track of basically the same things. We're keeping track of a node E. We're going to keep track of the head of list. private node e head, private node e tail, private int size, right? All those things you'd expect. And we're just going to create, and again, we're going to create basically the exact same constructor. So what changes here basically is the add method and the remove method, because now we have to deal with twice as many pointers to move around. Now you might think that this makes it twice as hard. It only makes it twice as long. What's nice about this is that there's more ways to actually do it, and less way. And there's less ways to basically make a fatal error, right? Because now you can go backwards as well as forwards. So actually, we get to choose. We get to choose, make some choices. So double linked list, taking nothing. Its head is going to be equal to null. The tail is also going to be equal to null, unsurprisingly, and the size is going to start at 0. So let's go ahead and write our first add method, which is that we are going to write the one that doesn't do anything except call the other one. So public boolean add e item, and that's just going to call the second add method, which will say it's going to take in size item, right? That's all that one's going to do. It says, of course, that doesn't exist, so we'll go ahead and return false. Nope, wait, it's supposed to be true. This is what happens when I try to type and think at the same time. Okay, so we'll go ahead and let Java create that one. So public void add, and tries to figure out what the variable names are going to be based on what I want. Well, first off, I want it to be public, and I want it to be index I'm at. So I'm adding a node to the index. So let's go ahead and list again our 5 conditions. So out of bounds, right? That's the first condition. Second condition is adding first item to list, like first item to empty list, right? Adding new head, adding new tail, everything else. Those are our 5 conditions, 5 if-else statements, and then we should probably remember to put size ++ right over here. Probably a good thing not to forget that, size ++, right? To remember to increment the size at the end. So once you have these 5 subproblems, right, when you get to your homework, you can work on these 5 subproblems one at a time, pretty much, right? That makes sense to everybody? So let's go ahead and work on out of bounds. So what are the valid indices? Well, they're the same thing for all the other add methods we've been doing for array list and for the single A linked list and for the double A linked list. It doesn't change here. If the index is less than 0, we can't add an index to negative. We can't add an item to index -1. We can, however, add it to size. So if it's greater than the size, because we can always add, because that makes sense. We can't, if the size of the list is currently 0, if this condition was greater than or equal to size, then we could never add something to the very first item to the list. If the size was 0, we'd have to add something to index 0, and then it would fail, and that would be terrible. So we need it to be size always needs to be something a valid index to add to. Okay. So throw new index out of bounds exception. Okay. Adding the first item to an empty list. Okay. So let's go ahead and write up our conditions. And these all have to be mutually exclusive conditions. In other words, they need to be a series of if, else ifs, and then an else on the end. So if the current size of the list is equal to 0, right? That means the list is empty. Else if, let's go ahead and put this over here. Else if adding a new head, well, where would we want to add a head? We'd want to add it to index 0, right? So notice that we've got size up here and index over here. Okay? Else, if we're adding to a new tail, well, what would that be? That would be index equals to size, the very last possible index we can add on. Okay? And finally, everything else, well, all other conditions, we're just going to slap a nice else on there and not worry about trying to figure out the particulars. Okay? What else do I need over here? Oh, if I'm adding an item, right, I need to put it in a node. So I say that node e adding, and that makes sense. But I used to put node here because that was also 4 letters. So then basically everything I would type would be 4 letters inside there. But adding makes more sense story-wise, so we're going to go with adding. So new node e item. All right. So if it's the very first thing we're adding to the list, then there's really not too much to do here because its previous is going to be null and its next is going to be null, right? The only thing that we have to do is just basically let the list know it exists. So it's actually the exact same as the singly linked list. So this dot head is equal to adding, okay? And this dot tail is equal to adding. It's both the first thing and the last thing in the list, right? Now if we're adding a new head, let's go ahead and draw. Always try to figure these things out first by drawing them. Don't just try to write wildly there, okay? So if I'm adding a new head, right? So also when I'm drawing, I always like to have the node this node the node at index 1 right there. So I always like to have one more than I need, and then I can just put some dots to remind me that there are more things in the list, right? So this is the head of the list, and now I need to have this node, which we call adding, become the new first node in the list. So the same rule fortunately applies here for us, which is that the first thing I want to do before I adjust the variables when I'm adding a new node is if I have things to connect, then I connect them. Okay? So let's think about what I need to connect. Well, in the singly linked list, the first thing I did was I said that adding dot next is equal to head, right? I would connect adding to head. That seems like a great first step here. Okay? But I also have to connect it the other way around too. Right? No problem there. I just simply say that head.previous is equal to adding, right? So now we're fully connected, right? We're connected. The only thing that isn't correct about this is that we haven't updated our head yet, right? So now we say, just like we did in the first one, head is equal to adding. So let's go ahead and do that line by line. So head over here. So the first thing we need to do was we said that adding dot next is equal to head. So we would connect this node over here, right? And then we would say the other way around, which is head dot previous is equal to adding, right? Take the memory location of adding and store it in the current head previous pointer, right? Does it matter which order I do these two in? Or should it matter? No, really shouldn't, right? Doesn't matter if I connect this adding and head, they both can be accessed using a name, so it doesn't really matter. I can do head.previous, I can do the previous first, or I can do the next first. It doesn't matter for this case. Okay. And now the last thing I need to do is say that that adding becomes the new head. And remember what that does is that actually we don't have like them labeled like this. Instead, there's like a head pointer up here. It's just pointing to that node, and it went from pointing to this node over here to adding, right? So that's how we add a head to this list. Now tail, pretty much, if you understand adding to the head, adding to the tail should be fairly straightforward because again, it's the reversed. But again, it's always best to draw these things just to make sure that we're on the same page. So instead, what I'm going to do is I'm going to keep this guy up here, and I'll switch it. Keep this guy up here, okay, and dot, 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 right? So I've got this node adding, which needs to be the new tail. And this guy is currently the tail of the list. So what do I need to do? First thing I need to do is I want to connect the node I'm adding to the list. So his .next doesn't need to be connected, but his .previous does, right? Make sense? .previous connects to the tail. Then we're going to connect up this guy's pointer, the guy who's currently in the list. Make his .next point to the node we're adding, and then we make him the tail. So let's do those lines. So adding .previous is equal to tail, because remember, it's going to be the last. Adding is now going to be the last thing in the list, so its previous should be the current last thing in the list. Likewise, the current last thing in the list, its next should be the thing that's going to be the last thing in the list. And now we say the last thing in the list is the thing we are adding. That makes sense. That should hopefully make sense to everybody. So that's 4 of the conditions, and that really wasn't all that much more complicated. It literally added one line here, another line. It literally added one line pretty much to each of these. Okay, so for everything else, well, since I don't like thinking too complicatedly, let's just follow as along as basically as best as we can with the original one, which is that we had the node E before that we would grab, right? We'd grab the node, if we're adding it to a certain index, what we'd like to do was grab the node before that index. So this dot get node at the node, sorry, at index -1. Okay? So we'll start from there, and now we'll draw what we need to do. Okay? So I just want to put that there so that we're all at the same page. Okay? Okay, so we've got node over here. And same theory over here. We've got I -1, we've got I +1, and I'm adding to index I. I'm adding this new node over here to index I. I'll put it here so it sits nice and halfway between them, adding before. Okay. Okay, so again, what I want to do over here is that the same rules apply. I want to attach adding before I update the rest of these things over here, which means it's going to get slightly messy for a bit, okay, just because it's a bit non-planar, meaning I can't draw this without lines crossing over. So the first thing I would normally do is I would just simply say that adding.next attaches right over here, right? And then if this was a singly linked list, what I would do is that I would attach this over here, and then it would be added to the list in one direction, but the other direction would skip it over. So what we need to do before we do that is let's take this arrow, is that we need to take this arrow, right? I connected adding over here, and then I need to take this arrow and connect it over here, right? So let's go through this line by line, because each of those arrow movements is a single line. So let's first do this one. So this one was saying adding .next, it needs to attach to before .next, right? We attach adding .next to before .next. The memory location of before .next that gets stored in adding's .next variable. Okay. Okay. Now we need to take this arrow and put it over here. Okay. There's a couple ways to do this. Actually, there's a lot of ways to do this. So first thing we need to do is that we need to figure out. So first off, we know that basically that we're pointing whatever we just moved at adding, right? So we know that adding is going on the right, right? Right? This points at adding. So we need to figure out what we're storing adding in. And we're storing it in this guy's previous pointer. So how do we reference this guy? Before .next and his previous pointer. The guy that comes after the before node, his next the guy that comes after his the before node, his previous pointer should now point to adding. Okay? Of course. Let's go ahead and see over here. Skipped a step, but again, I should probably attach adding to before over here, like this first. But, as I mentioned, with doubly linked lists, you get a chance to make a mistake like that, and it's not going to completely kill you here. All right, so let's go ahead and remember, adding.previous is going to be before, right? That makes sense to everybody? So I'm going to go ahead and put that in over here, beforehand. Adding.previous is equal to before, right? And that makes sense. These two lines make sense. Adding.next, it attaches to before's .next, and then adding attaches to the guy who's going to come before him. Okay. So now we've got before.next.previous attaching to adding. So the guy that comes after before, his previous attaches to adding. And now we need to attach, and now we need to attach the very last, this last over here, which is before.next. It needs to point to adding. Now, in case this is making your head spin a bit, and the only reason it's not making my head spin is because I've done this like a bunch of times, right? Your homework with the circular linked list, it's going to be a singly circular linked list. So links are only going to go in one direction. They're not going to be bi-directional. So, okay. So adding before. So now, right now, we attach adding to the node that comes after it, and to the node that will be coming before it. Then the node that comes after the node before the node we're displacing is going to point to adding, and then the node before is going to point to the node we're inserting. Okay. So let's see. There's also another way to, because of the way we've attached this also, there's, interestingly enough, another way to reference this. Adding's .next.previous pointer, because remember, before.next and adding.next now point to the same guy. So we could do adding.next.previous.adding. So there's a lot of ways to refer to these things in AA linked lists, because that's just the nature of what happens when you can go backwards. Turns out that going backwards means everything gets complicated. Okay, so let's go ahead and test this out to make sure that I'm not, pulling a fast one on you, because I hope to God I'm not. Public static void main string args. Okay, double linked list L is equal to, let's go with doubly linked integer is equal to a new double linked list of integer. Okay. L dot. Sorry. So let's see with 4. So let's go with L dot add 0 to the end. L dot add 1 to index 0. All right, so we're going to test all 4 of the addition. We're going to add to index to the tail end of the list, so we've got 2 things in here. So size 2, 2. So we should add 1, 0, 0, 2, 2, and then L dot print line L. So let's go ahead and make sure we're doing everything. So I've done everything but the last condition now. 0, 1, 2. So let's go ahead and make this 0, 1, 3. And let's go ahead and add to index 2 the number 2. Okay. Well, that seems to be working just fine. All right. So that's the add method for the remove. For the double linked list. And it wasn't. I mean, the only thing that was particularly annoying was this one, right? Because you had this before.next.previous, and that was kind of weird. So just wait, it gets really bad in the remove method. So I'm going to go ahead and steal most of this, and I'm going to rename it. Okay, because again, for remove we have 5 conditions, but the conditions are slightly different. So first, let's go ahead and you know what? Because people will be frantically typing and they can't copy and paste, I'll do void e remove int index, right? Okay, and we'll need a size minus minus on the end. We'll need to return something, so we're going to create an e to return is equal to null. Return to return. Okay, now what are the conditions we need to worry about? So the first thing is that if it's out of bounds. So if index is less than 0, well, we can't remove something there. Or if the index is greater than or equal to, is greater than or equal to size, then that's an index we can't remove. So we're going to go ahead and throw new index out of bounds exception. Okay. Then we have four conditions over here for things to remove. Now, because remember, these things are symmetrical. Now here, it was adding the first item to an empty list. So it's not removing the first item in an empty list here, though. Here, the condition is, what if we are removing the thing in the list? That basically, what if we're removing the last thing in the list? So if size is equal to 1, then we need to make sure that we are getting rid of both the head and the tail here. Basically, we're making sure that head and tail get set to null. We didn't have to do that previously in the other remove methods, but we have to do it here because otherwise it's not going to work. And I'm going to actually put here okay. So now we have our other conditions. Else if we're removing the head. So these don't really require any translation at all. Else if we're removing the head. Else if removing the last node in the list. The last node in the list isn't located at size though. If it's equal to size minus 1, right? That makes sense? We're removing the last thing in the list there, and then else removing everything else. any other node in the list. Okay. So let's go into this. So if size is equal to 0, size is equal to 1, right? Then the head and the tail are the same thing, and they both got to get set to null. So let's go ahead and say first let's save the item. To return is equal to head.item, and then head is equal to null. This is the first time we're basically deliberately setting stuff to null inside here, but this is the only way to get rid of it. And then it still exists because it's still the tail, and we got to get rid of it, otherwise that might mess stuff up. Tail is equal to null. Okay? So now it's gone, everything is gone, and we'll just return the last item that was stored in the list. Okay? What if the head was 0? Then we got to remove the head. So not only do we have to set head equal to head.next, but we also got to make sure that that basically the previous gets set to null. And same with the tail. We got to make sure that it's no longer pointing to the tail. So let me go ahead and work on one of those because I have enough time left for one of those. Okay? So suppose we're removing the head of a list, of a doubly linked list. Okay? Okay. This is currently the head of the list. So the first thing that's interesting is that I can just go ahead and make this node the head of the list, right? Because I can go backwards and forward, so it doesn't in the list. So it doesn't really matter that things that I can do this in this order. So head is equal to head.next. But we might want to just also save the item inside of head first. So to return is equal to head.item, and then head is equal to head.next. So now we're at this state where we're still attached, though. So the way we need to do that is, well, if it's the head of the list, I should be pointing to nothing as my previous node, right? So I got to erase this link. So I say that now the current nodes, so the head is currently the node that comes after head. So now we need to make sure that it's not pointing anywhere. So head.previous is equal to null. So we erase it like that. Okay. That didn't take nearly as long, so let's go ahead and do the next one. Okay. So next one, we need to, what if we're removing, oh, and what happens over here, by the way, because you might go, well, don't we have to set this guy's next to null? And I'm like, no, because this guy's going to get garbage collected. Nobody's pointing to him anymore. Okay. So now let's go ahead and say that this guy is the tail. All right. And he's got a node pointing over here. Keep the arrows the same way. Okay. So now we need to remove the tail. Tail is at index size -1. So again, what we're going to do is we're going to update this guy to become the tail. Right? We're going to say that to return is equal to tail.item. Right? And then we're going to say tail is equal to tail, not tail.next because that would be null, but tail.previous gives us the previous item. There. Okay. And now, this guy's now tail, so now we can just remove him. Sorry, we need to basically make sure that we remove the original tail. By saying tail.next, it's not going to point to what was the former tail, it's going to point to nothing now. So we can remove basically the forwards, the fronts and the backs. So again, notice over here the order of the time, the order of magnitude for all these operations. In both the singly linked lists and doubly linked lists, adding anywhere just adding to the either of the tail, to the head or the tail, which is honestly the most common place you add items to, right? Normally you add it to the front or to the end of the list. Very rarely do you add into the middle. Adding to the front and the end of the list for either linked lists took constant time. Middle, you'd have to scan through basically half the list, maybe on average. So if you're adding into the middle of the list, you have to scan through half the items, which is a linear time operation. Same with remove, though. Remove, this is a constant time operation over here. Removing here, the first item is a constant time operation. Removing the last item is a constant time operation. And so removing from the middle, though, we have to seek it. We have to seek for it, and we find it, and then we can remove it in constant time. But that seeking operation is a linear time operation. So removing anything in the middle takes linear time. So that's where we'll leave off on this. So on Wednesday's lecture, come prepared for a short quiz, that you can do electronically, and then we'll be finishing up Chapter 2. So that means that hopefully that the week afterwards we should have our first exam. And then we're going to do Chapters 3 and 4 probably next week, and those will go by like that. But we'll see. If I want to do something special for that week, I'll let you guys know in advance. So we'll see what happens, because those are pretty easy operations to do. I'll let you know if it's next, and I will definitely let you know if it's next week or the week, or if it's going to be week 5 exam or week 6 exam.